Okay, so welcome
Hello.
everyone. Thank you for being here for this second masterclass of the Plan B program for the developer track. Today we have Michel, aka KetoMiner, for that he would be speaking about the internet infrastructure in particular. So I'll let you present a bit yourself, and you can start with your presentation. Also, the presentation has been shared via the screen, so we will follow with you. And if we have any trouble for the student, I will share the presentation file directly with the other student.
Oh, thank you. Thank you for the introduction. Just one quick note, please don't hesitate to ask questions while the presentation is going. It's very, very technical, very densely packed. So yeah, really don't hesitate to interrupt me. I will try to be reading your messages and answer the questions as they come. So I'm Michel. Some people might know me as KetoMiner in the Bitcoin space, and so I'm present in the Bitcoin space as the co-founder and CTO of Nodl. Nodl is a company building Bitcoin full nodes since 2017, and we also host and provide server infrastructure for Bitcoin companies. I'm also running a project called Host for Coins. It's a little more underground. It's also hosting anonymous VPS hosting paid with Bitcoin and Lightning only. And I have a consulting company called Precision Labs, which I just created to take over my consulting activities. And this company is specialized in building infrastructure and helping other people build infrastructure. And by infrastructure, I mean servers and networks. Cybersecurity and space systems, especially the ground segment, what is called the ground segment of space systems, meaning everything that is not flying in space, and anything behind the antennas, and transmitting, receiving data over space connectivity. Someone mentions there is an issue with the sound. Can everybody hear me well?
Yeah, we can hear you well. There's sometimes
Okay.
an issue with the browser directly.
Okay. So there are five main parts in this presentation. So yeah, this presentation is about the history and the architecture of the internet, and a few interesting and funny things that can be done with it. There are five chapters: the origins, networking fundamentals, deep dive, trust and security, and implementation. So let's start with the origins and why you should care at all, being a Bitcoin developer, about how the internet is built. As far as I'm concerned, I believe that to fully understand the system, which is Bitcoin, you have to understand the underlying systems, which is the internet and everything that goes on top of it. Also, because network level attacks and network errors are real, it's really a thing. It happens all the time. In 2018, there was a hijack of MyEther wallet, which led to many people losing money. Telecom Malaysia misconfigured their network and became the whole internet for many people. I will go into details later of what happened. Pakistan Telecom tried to block YouTube and instead redirected the whole traffic for YouTube to their network, taking down YouTube and saturating their own network for many hours. And also, I think this topic is very important because there is a lot of projects more in the crypto space than in the Bitcoin space to create a new decentralized internet. And I think this comes from a big misunderstanding about the fact that the internet couldn't be more decentralized than it already is. So is this thing actually decentralized? Which is why we are here today. The web services are concentrated. That's a fact. There is one Facebook, there is one YouTube, there is one Instagram. There is a couple of very big cloud providers like Amazon, Google, Microsoft. More and more people are moving from small independent websites to big hosting platforms such as Shopify, for example, for e-commerce. Me as the hosting company for small enterprises, I'm living this every day because I have customers leaving their own hosting. They have their own server, their own backup, their own responsibilities. And instead they are switching to one centralized platform, which is Shopify. And that hurts the internet, and it hurts its decentralization. We moved from something which was completely distributed. Everybody was hosting their own services in the very beginning to a few companies hosting most of the services. But we can address this part by using other cloud providers. There are thousands of small cloud providers, dedicated service providers, VPS providers. There are a few names on this slide. You can also host a lot of things at home on a Raspberry Pi or on a computer at home. If you have a fixed IP address, that helps, obviously, because you can point your domain name directly at your service. But there are other ways you can use a small VPS outside just to tunnel back the traffic to you, or use a tunneling service from Cloudflare, for example, to expose your own services on the internet. That's not ideal, not completely decentralized, but it's already better than using a big cloud provider such as Amazon. But if we look at the network itself, the internet network itself, it's a network of more than 100,000 independent networks. There is no central authority. There is no one network running the internet. Everybody, it's like in the Bitcoin space, everybody has the same importance, even if you are very small. So the infrastructure, as they call it, is totally decentralized, but our use of it is not. And that's what I want you to understand. Chapter 1, the origins. This is the first map of the ARPANET back then, which was a joint research and military network from the US government in the 70s. It was connecting some military facilities as well as major universities and a few other nodes. The first international link from the American ARPANET was to UK and Norway through satellite. You can see it. I don't know if you see my pointer. On the right side of the graph, you see London and Northstar, and not straight line going to SDAC. So this is a satellite link over the Atlantic. And back then, 56K was considered as a high-speed link, which probably, I don't know how old you are, but when I first connected to the internet, 56K was like the fastest modem we could get. But that was already in the end of 90s, beginning of 2000s. But in the 70s, 80s, for the internet, 56K was the backbone connection. After a few years, in 1984, Milnet, which was the military side of the things, split up, and the only part of the internet that stayed, the ARPANET that stayed, was the university research network. This is a more logical map. So you can see all the nodes we've seen before, like Stanford here, MIT somewhere on the right, and the type of computers that are running this network. So on the right, you have a few pictures. This is a Pluribus computer. This is a S360 IBM, S370, little more modern, and the PDP-11. So these were like the state-of-the-art computers running the internet in 1977. And you can find again this transatlantic link through satellite here to Northstar in Norway and then to London. Fast forward to 1983. This is where we switched to TCP/IP, which is the protocol most of the things on the internet is using now. Anything internet related is defined in RFCs, request for comments. Is text documents that first start as drafts, and once they become a thing, they get a number. Think about the BIPs, Bitcoin Improvement Protocol documents. It's exactly the same. The BIPs are actually based on the RFCs. So yeah, the TCP/IP is defined in RFC 801, and we will see a couple of other numbers later. In 86, NSFNet, which is this new independent of Milnet network, connects major universities with a 56K backbone. 88, we upgrade to T1. T1 is 1.5 megabits per second. And in 91 to 95, so originally this network wasn't supposed to have any commercial use, but from 91 to 95, it was progressively open to commercial use, and the old NSFNet backbone was phased out and replaced by private companies. 95 marks also the arrival of BGP4, which is the dynamic routing protocol used today everywhere on the internet. It hasn't changed since 95. The way the internet, I really want you to remember this part. The way the internet works hasn't changed since 95. Nothing changed. And it scaled to more than 100,000 independent networks. Why TCP/IP is important? Maybe you heard about circuit-based networks versus packet-based networks. Circuit-based, think about the old telephone system. When you make a call, when you dial a number, each part of the number actually tells the switching equipment which place to connect you next, like a country, region, city, and receiving side. Originally, it was electromechanical devices. So when you had an impulsion-based phone, when you were turning the dial, you turn to 3, it sends 3 clicks over the line. And at the other end of the line, in the commutation center, there is a needle that moves 3 spots to the right, and then 4 spots to the top, and so on. And once you finish a section of the phone number, it goes to the next needle, and so on. So you had like massive rooms full of these mechanical devices. That's just after the switchboards with operators switching, plugging wires in the board. So once you finish dialing your number, your call is connected to the phone of the receiving person, and the circuit is reserved for the whole time of the communication. When we switch to digital and computer to computer, machine to machine communications, that means that to establish a connection between 2 computers, you have to establish this channel, and this channel stays open, whatever happens, even if there is no traffic. That's a circuit switch network. And if one hop in this chain breaks, the whole communication is down. We have to redial, and there is only one way usually to go from point A to point B. In a packet switch network, the decision is made for every packet. Usually on the internet, the maximum size of a packet, which is called MTU, is 1,500 bytes. Your communication is cut into packets of the same size, except the last one, obviously, because it's usually smaller. And each packet can follow a different route. So for each packet goes to the next router decides where to send the packet next, and so on, until it reaches the destination. That means that the resources are reserved hop by hop instead of end to end. If a packet is lost, it can be retransmitted on another route. But it also means packet can arrive out of order. That's the theory, because in practically it's very rare that the packets will follow different paths in real life, but the design allows for the packets to follow a different path for each packet. So the packets can arrive out of order, and as you can probably see, there is no resource reservation. I mean, you know how big the link is to the next hop, but you know nothing about what comes after. That means that in a packet switch network, you can't guarantee the bandwidth between point A and point B. And if there is a failure on the way, the packets will just follow another path. We'll see some examples further in the presentation. So the take out from here is the internet is a packet switch network, and it was designed as so because the United States wanted a network that can survive a nuclear blast, destroying parts of the network, so reroute around the nuclear attack. Nowadays, we have higher level protocols such as segment routing or MPLS that can provide circuit-like reliability on top of the switched network. So we can actually build circuits end to end. You only see the entry and the exit over a TCP network under it. I'm meeting a lot of people who believe that the long distance connections are made over satellite. And if we were still in 71 to 73, that would be true, as I showed before. The only transatlantic link was a satellite link. But actually, the long distance communications are mostly cable based since 1858. The first transatlantic telegraph wire was laid in the bottom of the ocean in 1858. And in 2024, we had about 550 submarine cables for 1.4 million kilometers in total. The capacity of one cable is hundreds to thousands of terabytes per second. The capacity of one satellite link is in the gigabit per second scale. So we're talking a completely different scale. And what is very interesting about optical cable communication is you probably know that there are amplifiers on the way, like every 80 to 200 kilometers. On the cable, there are capsules with a light amplifier. And what is very interesting is that these amplifiers don't care about what type of signal goes into them. Meaning that a cable that was doing 1 terabyte 10 years ago can do 1000 terabytes today with the same amplifiers. You don't need to upgrade the cable to upgrade the capacity because it's a photonic amplifier. So they will just take a decaying photon on the entrance, amplify it, and send it on the other side. Doesn't matter how many, doesn't matter how fast. Also, if we were using satellites to cross the Atlantic, it would take 600 to 800 milliseconds round trip time. RTT is round trip time. Using a cable, it's 55 to 75 milliseconds. So not much faster. And the cost per bandwidth makes satellites totally impractical for long distance communications. If any of you try to subscribe a satellite phone service, it's north of $1,000 per month, usually for a subscription. These cables are owned mostly by consortiums of telcos, telecom companies, and a few recent ones, which are, I think one got delivered and the other ones will be delivered like next year or in 2028, are owned by Facebook, Google, Microsoft, and so on, but mainly by telecom companies. Do we have a cable in the Pacific Ocean? Yes, more than one. Give me just a second, actually. I'm linking this website later, but I will just show you right now so you see what we're talking about. So if we're talking about the Pacific, we have a few cables, yes. Surprisingly, one of the major hubs of undersea communications is Marseille in France, because it's a very strategic point to go around Africa, east side and west side. Cost per kilometer, I wouldn't say. I really have no idea. I'm sorry. Okay, I'll go back to sharing the presentation. So I said mainly internet is not using satellites, but everybody knows Starlink. So what is Starlink? Starlink is not part of the internet backbone. Starlink is a internet access provider. Same as your mobile phone company can provide you access to the internet, same as your home internet is an internet provider. The only thing that changes is the last mile connection, which is more than a mile in this case. But at the end of the day, the traffic goes up to the satellite, down to the ground station, and then to the internet. But the internet, say the internet backbone stops at the ground station from which Starlink connects the satellites to you. One quick mention I didn't put in this slide, you might have heard about Blockstream satellite. Blockstream is renting some capacity on telecommunication satellites to broadcast the Bitcoin blockchain. These are basically TV satellites. They can do broadcast only. So same story here. There is a ground station somewhere taking the Bitcoin blocks from the internet, repackaging them in a special way and sending them up to the satellite, which then mirrors them down to the floor. And with 80 centimeters antenna, you can get the Bitcoin blockchain as receive only from this satellite. So there are probably still a few islands connected only by satellite to the internet, but that's how far the internet backbone through satellite would go. Everything else is cables. And even if you look at you'll find the link to the map in the presentation. If you look at the map, there are some tiny islands already with cables connected to them. As soon as there is a cable coming close, we can make a split and go out of the cable to the island. So. I just mentioned internet access providers. I don't like the English ISP term because it's too generic. In France, we have a term called FAI, fournisseur d'accès Internet, which means internet access provider, which much better explains what Starlink, what your home ISP, what your mobile phone company are. They give you a point-to-point connection into the internet. An ISP can be in English can be many more things. A hosting company is an ISP, a telco is an ISP, your home internet provider is an ISP, and actually in a typical big ISP, if we take I don't know AT&T or Orange or companies like that, they will have two separate networks, one as an internet access provider and another one as their worldwide interconnection network. To that, I will throw at you a little vocabulary. We will talk about it more later. A peering is a connection between two ISPs. In this context, two ASNs. I will explain what that is later. A transit is an uplink, is a special type of peering providing a full view of the internet. A full view of the internet is a connectivity which gives you all the routes of the internet. I will explain what that means a little later as well. A tier one network is a network that sees the whole internet only through peerings, meaning they don't buy and they don't need to buy any connectivity from anybody else. They're like the same level, the biggest networks in the internet. It involves being present on the whole planet, on all the continents. There is probably less than 10 of these networks. Then there are tier 2 networks that see close to the whole internet, but not everything. They have to buy some of the view, and they get the other one through peerings. Usually we'll be talking about regional big companies like European or American ISP that still needs to buy something from a tier 1 to get the view of the remaining parts of the world. And then all others, small companies like mine, like yours could be, who need to buy a view of the whole internet, and in addition to that, you will have some diversity through peerings or through multiple connections to a tier 1 or tier 2 network. And then we have internet exchange points. It's huge switches or networks of switches in which ISPs can interact and connect to each other. So the point of these IXPs is that, for example, there is 300 different ISPs connected to one, and once you connect to one port of the switch, you have access to all the other 300 networks. Of course, then you have to negotiate with every one of them to establish a connection, but you don't need another physical connection to access these networks. How it's going now? So there is not a single view of the internet. As I explained, there are different types of ISPs, different sizes, and nobody will be connected to the same other ones. So you will see every network will have a slightly different view of all the other networks. The NSRC made a nice map. I'm linking a PDF here. You can have a look at it later. When I first made a short version of this presentation, it was at Baltic Honey Badger in August last year, and I made a screenshot of one of my routers 2 days apart. So IPv4 routes, as you can see, the number increased. IPv6 routes, the number actually decreased. And it's not 18, it's 8 months later, actually. Now we have more than 1 million IPv4 routes and 230,000 IPv6 routes on the internet. But every router you will check, even if in my own network, if I go to another router, I will see a different number because it's not connected to the same networks, so it will have a slightly different view. All of them have access to the whole internet, but because, for example, some networks will be aggregated, others will not be. In some locations, I will have a different number everywhere. So chapter 2, network fundamentals. A quick reminder of the difference between a hub, a switch, and a router. Hubs, network hubs, mostly don't exist anymore. You might still find some old ones somewhere, but they won't typically be used or for very specific applications. A hub does something very simple. It takes a packet on one port and it sends it on all the other ports. This can lead to collisions. Some of hubs have a indicator on the front to show that there are collisions happening, because it just blindly sends everything to everybody. A switch is an intelligent hub. We also call that layer 2 routing with quotes. It receives a packet on one port. It looks up a MAC address table. It knows which MAC address. The MAC address is an identifier of your network card in a computer. So it looks up which port is connected to the destination MAC address and then sends the port to the packet to that port. It can also send packets to ask if someone knows this MAC address, but by default, if it doesn't know a MAC address, it will not forward the packet. I'm obviously simplifying things. There's things called multicast, which allow to send to many ports at once, but the basic functionality is this one. A router or level 3 routing takes a packet on one port. It looks at the level 3, so it looks at the destination IP address. It looks at its routing table, and it looks up the subnet belonging to this IP address, and it sends the packet to the next hop, so the next router in the chain. So for I have a small drawing of an example later. But the routers is what you will see when you do trust route command on your computer to another computer. The problem is most modern high-end switches can also be routers, and most routers can be made into switches. So many equipments now are hybrids and do both. We as network administrators try to separate these roles and avoid doing both on the same equipment, but sometimes we don't have a choice for budget constraints or just because we don't have the correct equipment in the correct place, or just because we need some very simple routing, which is okay on the switch, but typically we will not load like the full view of the internet on the switch. So I mentioned the routing table. What the router's role is to maintain one or several instances of routing tables. Directly connected is the easiest one. It's not actually a routing table. Is if my address is 192.168.0.something/24, it means that I can directly reach 192.168.0.anything on this network interface. A static route says to reach this destination, I have to use this gateway. So for example, this is me. I want to reach 192.168.10.something, and I know that I can do it through this host. So I will have a static route. On Linux, it will be root add minus net destination, GW for gateway, and this IP, and the traffic will go here. And usually you will have what is called a default route, which allows you in a home network to reach the internet, which means 0.0.0.0/0, which means everything or everything else. I can use gateway, and this will be your home router. So yeah, here I have an example where this computer allows me to reach some other network, and this is my home router, and this is the internet. Now imagine maintaining that for 1 million routes and updating it every few milliseconds. That's technically impossible, so that's why we have dynamic routing protocols. What a dynamic routing protocol does is very simple. It allows one router to say to the next, I know how to reach this destination. That's all it does. And a million other ones. Internally, we'll be using interior gateway protocols. Usually it's RIP, ISES, OSPF, and so on. Externally, most exclusively BGP. Actually, for most usage, we will be using both OSPF and BGP as IGPs, but I will not go into details how that all works. But yeah, if you want to discuss that one day, I'll be happy to go deeper on this subject. But yeah, just remember that there are internal routing protocols and external routing protocols, and usually external is only BGP. To do BGP, you need a AS number, ASN. What is an AS? It's usually an organization or a part of an organization defined by a number. This number is like a ID of your network. Let's say like postal code. It's not a very terrible, not a very good analogy, but I can't think of anything better right now. So the RFC 1771 in March 95 defines the concept of autonomous systems and BGP4, which, as I said, pretty much nothing changed. It's still used on the internet everywhere. So what you need to remember about the AS, autonomous system, is that it has to be in one piece. It can't have hosts. So it means that all the routers of one AS have to be interconnected physically with each other. It can be over long distance link, doesn't matter how far, but you can't have the same AS number in two places isolated from each other. And yes, so as Nodo, I'm running 2 different autonomous systems, and for my other companies, I have 2 more. and I'm managing a lot of additional ones for my customers. So yeah, the quick way to remember that is one ASN equals one ISP equals one participant in the global internet. We used to use 16-bit ASNs. There are still a few available, usually because they were freed by someone. You can specifically request one 16-bit ASN when you ask for a number. Usually you have to justify it by having some old equipments that don't support 32-bit ASNs, which is usually not true, but yeah, the smaller the better, so we like small numbers. Currently, by default, you will get a 32-bit ASN assigned. I think usually they start at 126 and then 3 digits. I've seen some 206 as well, I think. But unsupported on older equipment, that's not a big deal, but actually you only need to support what the next hop announces you, and if there are some 32-bit ASNs further down the line, it doesn't matter. And the same as we have private IP addresses for internal addressing or for experimenting, we have private ASNs. These are usually used when you have only one upstream and you don't need to be visible as an ASN on the internet. Your upstream ISP will give you a private number which you can use to announce your IP addresses to them. And there are 5, I think, except ARIN, which might be a company, the 4 others are non-profits, managing the attribution of ASNs and IP addresses in the world. Le RIP, NCC, so the name is half in French, half in English, Réseau IP Européen Network Coordination Center, covers Europe plus parts of Middle East, like Israel, Iran, Iraq, and so on. ARIN for North America, APNIC for Asia Pacific, LACNIC for Latin America, and AFRINIC for Africa. Each one has a pool of ASNs and of IP addresses to assign. I think only APNIC and AFRINIC still has any IPv4s to assign. So unfortunately, they are being drained by foreign companies who create an ISP in their region just to get an assignment and then move it over to their region after the 2 years, because you have to wait 2 years before you can move a subnet to another regional internet registry. In the European zone, you can subscribe to RIP and get on a wait list. Last time I did it for a customer, we waited 3 years before getting an IPv4 block assigned. What is important is why we need IP blocks is, so as I told you, the IPv4 internet already represents more than 1 million routes and it's getting more and more fragmented. The minimum size you can announce is a /24. Everybody will refuse a smaller subnet than that, so you need to get at least a /24 to be part of the internet and announce your prefix. And for IPv6, the minimum is /48. So IPv4s can be obtained via waitlist or secondary market. They retail for a /24 from, let's say, even from 8K to 15K, depends where you buy and how fast you want it. You can also rent blocks, but I don't advise that because usually the people who rent out blocks, unless it's a well-known company, they are used for spam and you will be blacklisted pretty much everywhere. IPv6 is mostly free because there are more IPv6 IPs than atoms in the universe. But you still need to be a member of your local regional internet registry. So you need to become a LIR, a local internet registry, which also gives you an ASN. And that costs, for example, in the RIPE region, €1,000 one time and 1,800 per year. Plus 50 for each ASN, and something for IP4 locations as well. But yeah, it has some cost, but that's what makes you a member of the internet. Back Then we also had PI subnets, provider independent, which could be multi-homed, so connected to multiple upstreams without yourself becoming a local internet registry, but that's basically gone now. Let's have a slightly deeper dive. So BGP, RIB, FIB. That's RIB and FIB are very important concepts. BGP now is directed by a slightly newer RFC 4271, which supersedes 1771, but it doesn't change a lot. What BGP does is only telling your partner network, I know how to reach that destination. It uses TCP port 179, and it's a state machine, which goes from idle to established. You can see a small diagram of the state machine here. And as you can see, there is no end in this diagram. And actually, there is no way to cleanly disconnect a BGP session. Usually what will happen is you have to send withdrawals. So you send your partner network, you say, I'm stopping to announce this, and this for all the routes you're announcing, and then you just drop the TCP connection. But if your link gets broken for some reason, or someone pulls the cable and disconnects you, the network on the other side still thinks they can reach you, and vice versa. So on top of that, we use something called BFD, which can very quickly detect the disconnection and stop the BGP connection, even if the drop is unclean. The RIB is the routing table as it exists in your routing software, not in your kernel or hardware. Meaning, if you have a router with two full views of the internet, you will have two instances of the RIB, and you will have two routes for every subnet. And then your routing daemon will decide which one is best and insert it into the FIB, forwarding information base, which can be all hardware if you are rich and buy a high-end Cisco router, or in your kernel if you're like me and you're using a Linux or BSD box as your router. So in your kernel, you will never have more than the million routes, but in your RIB, you need enough memory to keep multiple routes for each subnet. Usually on the Linux system, you can survive right now with 4 gigs of RAM for a full view router of the internet. But on ASIC-based routers, you will probably need 16 gigs of RAM minimum right now to run the whole internet. So I said the networks are identified by ASN, and to reach a destination network, you will usually be going through more than one other network. So this route will be called an AS path, which is different from a trace route. A trace route will show you all the routers you are going through. I think if you run on Linux trace route minus A, I'm not sure. You will actually see the AS numbers near each hop. You can just do man traceroute and you will find how to do that. So for example, from one test network I did, let's look for the route to go to this destination. The route goes through these 3 networks, which means I'm connected to 2914. 2914 told me to reach this destination through me. You'll continue through 1916 and 2716. Why we need this AS path is first because shorter usually equals better, even if it's not completely true, because as I said, you can have multiple hops in one AS. For loop prevention, you should never see your own number in this path. It would mean that the traffic is coming back at you at some point. That's also why you can't have a disjoint AS. It has to be continuous because the traffic can go out to another network and then back to yours. And also for debugging. For example, recently I had a case where I couldn't reach Amazon in Ireland. through 5511, which is Orange International. Orange International was still announcing routes to Amazon, but their uplink to Amazon was completely saturated, so the traffic was not going through. So yeah, that allows you also for debugging and deciding, for example, that okay, now I want to reroute traffic to Amazon through another provider because this one obviously has an issue. Route selection is in BGP is more or less always following these priorities. The truth is 2 and 4 are probably the most important ones. When you receive a route, you can assign a local preference to it on your inside of your network. For example, 800 for an IXP because it's free, and I don't know, 200 on the transit which you are paying. Yeah, and so using the local pref, you can have a fine-grained control over your outgoing traffic. And if you leave the local pref identical, you usually fall on the shortest AS path. Also, what is very important is more specific always wins. So the smaller subnet always beats in the routing table the bigger one. So if you receive a /22 and through another link you receive the same IPs as 4/24s, this is which will be privileged by your router. Your router will always select the most specific route, unless you specifically drop this because you receive the bigger subnet, which is very complicated to implement. So this actually allows you to have some control of your incoming traffic. As I will explain in the next slide, it's very easy to control outgoing traffic, but very hard to control incoming traffic. But it also allows for hijacks. So for example, if Google announces some of their IPs as a /16, and I start announcing just a block which interests me inside of the Google address space as a /24, chances are that many people will get fooled by this and send me the traffic they actually want to send to Google. So this is what we call traffic engineering, short story about control. Very easy, as I said, to influence outgoing traffic because you can basically do whatever you want on the outgoing side. You can choose where you want to send packets to any destination network, at least on the first hop. Then you have no control of what happens next to the packet. You can use the information about what happens next as to choose which first hop you will be using, but you can't force it below the first hop. Someone is asking, can we say that this route system works kind of the same than the Lightning Network one? Yes and no. The Lightning Network one is much more complicated because it also includes capacity in the routing, which we don't do in the internet. That's also why I very publicly said that the Lightning routing problem is unsolvable because it's already very hard to solve when you don't take into account the capacities of each hop. And if you add that, it just becomes an unsolvable problem. So yeah, as I said, you can force the first hop of the traffic, but you can't force what happens next. That's usually used for control to control price and capacity planning. For example, I have 100 gigs on one side, 10 gigs on the other side. I know that I'm sending, let's say, more traffic to AT&T than to DTAG. So I will send all my AT&T traffic on the 100 gigs link and my DTAG traffic on the 10 gigs link by default. And if one goes down, it will automatically go through the other one thanks to BGP and having multiple routes anyway. But it's very hard to control incoming traffic exactly because it's easy to control outgoing traffic. The people on the other side do whatever they want. I can try to influence them, but I can't force them to send me their traffic through a particular route. So announcing more specific is the most efficient and working way to do that. There is also prepending AS path. So for example, if I'm AS1234, I will ask my router to add it many times. So 1234, 1234, 1234 in the AS path, and to make it artificially longer, but most people will be just stripping that anyway. So it's not very useful. So yeah, as I said, number of hops is greater or equal to AS path length because there is at least one router in each hop of the AS path. And the actual number of hops is usually greater than the number of hops visible in traceroute because some things are not visible in the traceroute. For example, if a network is using internally MPLS, you will see the ingoing router and outgoing out router of the MPLS circuit, but you will not see how many routers you're crossing on the way. A little more about transit versus peering. So transit is usually paid, provides you the full view of the internet, 1 million plus routes. You pay for bandwidth, not traffic. Paying for traffic is a scam. I know in some countries, even when you rent a server, it's normal to pay for the traffic, so gigabytes that go out of your server. But that's not what actually the ISPs pay between each other. So it's a huge scam. What you should be paying is the capacity of the link you are buying. So for example, let's say I'm connected to a network with a 1 gigabit per second link, and I say, okay, I know that my usual traffic doesn't exceed 100 megs per second. So I will say I want a commit of 100 megs on this 1 gigabit link. I'll be paying, let's say, 100 euro for 100 megs, and then anything that goes above 100 megs, I will be billed as an extra. That's called the burst. And the way we calculate that is called 95th percentile. We take all the values, we order them from the biggest one to the smallest one, we remove the 5% biggest ones, and then we draw a line, and this is what you will pay for the extra traffic. So that's what actually ISPs pay, and that's what Amazon pays to their providers when they buy network connectivity. They don't pay for each gigabyte going out of their network, but when you rent a server from Amazon, you pay for each gigabyte going out of your server. The peering links are usually free, but you may have a flat fee for using a port, especially if it's on an IXP, Internet Exchange Point. It's usually much cheaper than a transit, and then you have to agree with each participant in the peering point to establish a BGP connection. Usually you only announce yourself and your customers. You don't announce the whole internet on an IXP, except in a few cases where some IXPs allow reselling internet connectivity on the IXP, on the switch. But that's very specific. Usually they use a dedicated VLAN for that. It's very marginal. And then you can have a private peering, it's called a PNI, where you physically in the data center interconnect with another ISP and you have a one-to-one connection. That usually happens when you have a lot of traffic to one particular destination. As I said, the tier 1 networks can reach 100% of the internet via peerings only, so no money exchange, and there are a few names below, and there are not many more about that. Can I elaborate about the unsolvable Lightning network capacity problem? So it's a routing problem, not capacity problem, which are two different things. I think in the beginning of the Lightning network, we first imagined everybody will be peer-to-peer, will have a fully, no, let's say not fully, but very meshed network. Then we moved to a hub and spokes model, which basically has some very big routing nodes and leaf nodes connected to that, which kind of works. But the problem is the implementation of the routing algorithms. And if you want, if you're an adventurous developer, I think that's really something you could work on, because almost 10 years later, we still have very simple Lightning channels that don't work. For example, I have A, B, C, enough capacity between the three nodes. A to B sends payments, no problem. B to C sends payments, no problem. A to C can't find a route, even if it's obvious for anybody looking from outside. And sometimes it works, sometimes it doesn't. Yeah, it's very, very random, and I think a lot of research and work could be done to improve the routing in the Lightning Network. As is, I think it has limited to no future. Sorry for being pessimistic, but I think there are very brilliant developers who can come and fix that. So yeah, nothing unfixable, but right now, almost every person I know is using a wallet of Satoshi and basically doing Lightning over database and not over Lightning Network. Just a quick example. Yesterday I was in London in the Science Museum. They have a first switch of the London Internet Exchange on display. That's, if I'm not mistaken, is a 10 megs switch. So yeah, that's the very first switch of the London Internet Exchange. Nowadays, we usually see 100 and 400 gigabits per second ports on the network, on the IXPs. And they are usually not based in one location anymore, but there are huge fabrics of interconnected switches between many data centers in the whole in the same city, or sometimes even across several cities, which allows you to use them as a transport, long distance transport as well. And most IXPs, if not all, have what we call route server, meaning usually if, so on an ISP, as I said, you have to negotiate with every other ISP present if you want to interconnect. Some of them have an open peering policy, means they will peer with anybody asking. Some have a restricted or case-by-case peering policy. And some of them will be present on the route server. Route server is another AS number, run a BGP router, run by the Internet Exchange itself, to which all the participants who want can connect and exchange all the routes with all the other participants on the route server. The advantage of this is you have only one BGP session with this route server, and it allows you to receive the routes of many networks at once. And the typical traffic on the big IXPs now is tens of terabytes per second. You can go explore more. You can do some trace routes, some pings, some IS path queries directly on routers of many ISPs. Actually, they make them public. There are a few examples here. There are also websites like bgp.he.net, which allow you to visualize partial view of how the networks are interconnected. You can just type any AS number and see who they are connected to. Traceroute.org is full of broken links, but if you're patient enough, you will find some routers you can even telnet and run queries from. And you can also just type some AS number or ISP name and looking glass into Google or into any search engine, and you will find pages like the one on the right, which is from Orange International. You can choose a location, and then you can do BGP queries or trace routes from any of the routers publicly. And then if you want to experiment without paying and without participating in the real internet, you can go to dn42.eu, which has all the features of the real internet, but in a sandbox based on VPNs. So you can run a bunch of routers at home and connect to this network. As I didn't mention yet, the routing is mostly asymmetric, and unfortunately, I have only an example where it's actually is symmetric. I made a trust route from Rio to Paris and back. This is one way. This is the other one. So we go through the same networks, except in the back route, we see one more possible path. So this is a graph of all the possible paths to go through here, to go from here to here. As you can see, there are many, and the green one is the selected one. And in this case, in the other direction, the same paths got selected. It's actually, sorry, this graph is from the right to the left, and this one is from the left to the right. And here we can see that in addition, we have this, which means that they probably buy connectivity from this network, but this network doesn't re-announce the routes learned by this network. That's why it works only in one direction. I will address your next question later after we talked about some of the attacks on network. So trust and security. This is a very important concept. As you probably noticed, a lot of things are made peer-to-peer. So we just contact the other ISP, ask them, do you want to peer with us? And then we exchange a bunch of routes and we trust what we receive. And by default, BGP is trust, don't verify. So some ISP sends me routes, I just accept them and I believe what they what they tell me. So if some peer tells me I can reach 8880/24, we will send them the traffic to that IP address. Another one tells me that they have a quicker path to AWS than anybody else. I will send them traffic to AWS. Why this mostly works is because it's a very small community. I would say less than 10,000 individuals in the world are managing the whole internet. Reputation matters. If you are a bad actor, you're very quickly shamed and disconnected. And most of issues happen because of mistakes and not because they are malicious. From all the examples I researched for this presentation, you will see there is only one which is actually malicious. Incident number one, the Telecom Malaysia incident. AS 4788 accidentally announced 179,000 prefixes to level 3. Back then, the total size of the internet was probably 500,000, so it's a big part of the internet. And level 3, one of the tier 1s, accepted and propagated these routes to all their other customers. That led to a global internet slowdown. A lot of traffic was sent to Telecom Malaysia, which basically became inoperant, and mostly affected APAC, fortunately, and the level 3 internal network. Why it didn't affect other regions? Because the links to Telecom Malaysia are so small that it quickly just shut them down. This is how it looked. So massive route leaks cause internet slowdown. This is a graph. I don't have the scale, unfortunately, because I took this from a presentation I made 10 years ago. But this is how it looked on my graphs. These are the updates per second, the BGP messages received per second. Usually when you see something like this on your graphs, it's something standard you can get from any router, BGP updates per second. Oh, okay, I took it from this article. The graph below shows the packet loss. No, this is not this graph. Yeah, no, sorry. Yeah, this graph is not the one mentioned in this article. This is a graph from my router. So yeah, you can see many more BGP messages per second than usual. Usually when you see something like this on the graph, something is happening. This is like the background noise of the internet. there is always some network failings or disconnecting, reconnecting somewhere in the world. Since you see all the 1 million networks connecting and disconnecting, there is always something happening. But when it goes from like 5 to 10 per second to 100 per second, you know that something is going on. The YouTube incident, that one was pretty fun, and I remember actually experiencing it in real time. Pakistan Telecom wanted to block YouTube domestically, so what they did is called a no route, meaning they routed the traffic to YouTube to their own network. Usually you route it to a black hole network, but they routed it to their own network. And they announced this route to their upstream, PCCW, who propagated it globally. PCCW was at the time a tier 1 network. So this one practically shut down YouTube for the whole world for 2 hours and sent all the traffic which was supposed to go to YouTube to Pakistan. Again, no malicious intent. Of course, one could say that trying to block YouTube in your country is malicious. Yes, I agree with that, but the point was not to get all YouTube's traffic to their country. It was to just block their country from accessing YouTube. Facebook incident, that one is pretty fun, 2021. Recent one was still during some level of COVID shutdowns, which makes it really which is why it happened how it happened. BGP misconfiguration in Facebook's network, 6 hours downtime because nobody was in the office. They did it remotely, and they fucked up their own office's network by doing so. And those access control devices were on the same network as their production network. So the history says that they had to force their way into the offices to fix the problem. And the losses estimated to $6 billion. I don't know what that means in real money, but that's Facebook bullshit revenue money. This one is really malicious intent and is the closest one to crypto I could find. There isn't a similar incident in the Bitcoin space yet that I know of. Don't remember which year this was, but the malicious actor at a small ISP or a client of that ISP announced Route 53, which is Amazon's DNS service IPs, with the goal of redirecting traffic to MyEther wallet to themselves. So they didn't attack MyEther wallet's IPs directly. They announced Route 53 IPs to answer bogus DNS requests with their own IPs and redirect traffic to MyEther wallet to themselves. And that combined with the fact that you can very easily buy an SSL certificate for someone else's domain name made MyEther wallet work, and yeah, they managed to steal 150K from MyEther wallet users in Ethereum, which is not much, but it's a very cheap attack actually. So the defense for that is extensive filtering. There are tools to build filters based on what ISPs put in the regional internet registry databases. So you know who is for domain names. There is the same for IP addresses and for objects of regional internet registries. If you type man whois on your computer, you will see that there are flags like -r, which allow you to query the regional internet registries instead of the domain name whois servers. By default, it tries to automatically guess if you run whois and an IP address or whois AS and an AS number. It will try to find the correct registry to query, but sometimes you have to force it manually. Not yet. That's one. So there are what we call route objects, which link one IP block to one ASN. These are quotes mandatory. Normally, any BGP announce that doesn't have a route object should be refused. That's mostly the case now. People are building filters daily, so I have cron jobs that will query the database and update their filters daily on the routers. There are other basic filters such as max prefix. For example, you're connected to an ISP which has 100 subnets. They have no reason to send you 100,000 subnets like it happened with Malaysia Telecom. If level 3 had this basic filter, this incident would not happen. The BGP connection would have been broken the second Malaysia Telecom started announcing that too many prefixes. There is also a list of routes called the bogons. You can actually connect to a bogon source with through a BGP connection, a multi-hop BGP connection through the internet, and it will be feeding you a list of subnets that shouldn't exist on the internet. That includes private subnets, 192 and 168, so on, 10.0.0/8, and so on. And also subnets that are not assigned yet to anybody, so they shouldn't be routed. But some smartasses try to use yet to be announced networks to get free IP addresses, and they just announce them and use them for spam also. ASPAF filters on length and content. You can limit, for example, you can say I don't want an ASPAF longer than 10 hops. And so on, and then BCP 38, best common practice 38 is another filtering policy. I'm linking a website later on which you can learn more about all these filters. Maybe that's a good moment to address your question. Well, to experienced eyes, I think it must be pretty easy to spot something like Lightning Network traffic, for example. About CoinJoin silent payment taproot, it's not really network traffic because you can very well build your transaction and broadcast it from a totally different place. I think Tor and maybe something like NIM fixes that part pretty much. I wouldn't, maybe can do a small segue about VPNs in the commercial sense of it, meaning this NordVPN and so on. By using these services, you're just shifting the place that can do traffic analysis from your ISP to an underpaid company with a much smaller infrastructure probably, and who has commercial incentives to analyze your traffic more than your ISP. So unless you want to defend against, if you live in a country where your ISP have only one way out and it's through government-owned fibers, example, Pakistan, Russia, China, and a few others, I would trust more any ISP over a VPN provider. And Tor probably gives them a solution to this problem. But then Tor is very easy to spot on the network, so they will know that you're using Tor and they can just come to see you to ask, well, why you're doing that. So as you can see, all this filtering is not very advanced, and it's not. So what we invented now is RPKA, PKA for private key infrastructure, R for route, and we use that to do ROV or ROA, route origin authorization. There are databases with signed messages that can certify that a particular ASN may announce a particular network. Doesn't mean it has to, but it means it can. There are 3 levels of validation. Valid means the entry exists and matches. Invalid exists and doesn't match. Route should be refused. And unknown means there is no entry in the RPK. The deployment as of 8 months ago was 50% of routes had these signatures, cryptographic signatures, and only 30% of networks actually check them, and 15% of the total, not of the 30%, but of the total, actually reject invalid routes. Meaning there is a lot of work to still do. It's progressing every day. It's progressing slowly because it's an investment. Many cheap routers can't do validation. Many older routers can't do validation. Smaller ISPs have no reason to upgrade their routers to new ones because it costs a lot of money. And by a lot of money, I mean a router, like the basic Cisco router used by a big ISP, costs about 500K each. And usually they will have tens of them. So we are talking millions of dollars investment to replace the routers. And honorable mention for BGP-SEC, which was supposed to secure the BGP protocol itself. It exists, and I haven't seen anybody using it yet. We are still using MD5 to secure the BGP connections router to router. So as I said, it's a small community, and there is an even smaller community called Manners, because we want to teach each other good manners. It's a community trying to... So we do a lot of name and shame, but we also want to praise the people who do good things, and Manners lists ISPs that implement proper filtering and proper anti-spoofing. So yeah, right now there is 1,000 plus participants. There is not any kind of enforcement. Anybody can do 1, 2, 3, or all of the 4 actions which are listed here. But yeah, you can look at this website, manners.org. It's pretty interesting. There is a lot of documentations linked there as well. So now let's go into the practical things, implementation, what you can do to become part of the internet, and what, in my opinion, anybody building a Bitcoin company using any kind of online service should probably be doing. 2 ways to see self-hosting. On the left side, we have a very American one. People have crazy home labs with tens of computers, switches, and all that connected to their Verizon fiber, or whatever that is. On the right side, we have a more European and my way of doing things. This is a quarter of a rack rented in a data center in Paris with a BGP router in the bottom. The black thing here, it has 8 10 gig ports, a small hosting cluster, a NAS, 2 switches because we need redundancy. So even if such a small rack, I have 2 Cisco Nexus switches, and this is my out-of-band management router. I have 4 different uplinks from here to 4 different networks. And I'm hosting a bunch of VMs, and this is also interconnected. So this is in Paris. It's also interconnected with my infrastructure in another data center in Paris, to Geneva and to Zurich. This runs an AS on its own. You can start small and iterate. If you already have a home lab, you can upgrade to an ISP with a fixed IPv4 address. If you can't think of one, or if you don't have one in your country or in your city, Starlink is always an option if you take one of their business plans. Unfortunately, it's very expensive if you do that. But you can turn the Starlink router into a bridge and have the your own IPv4 and IPv6 address on your own router behind the Starlink dish. But it's, if I remember correctly, it's 40 euros per month for 20 gigs, and then you pay, 40 gigs, and then you pay for each 40 extra gigs used. You can get a UPS, you can get a generator. An alternative to fixed IPv4, there are two alternatives. One was very early days internet. You probably have that on any NAS or router device you have at home. Is to use a dynamic DNS service, dynamic DNS. So basically, each time your IP address changes, it will update a DNS record to point back at you. But that's not instant, and yeah, if you can tolerate some downtime, that's a good way for hosting things. And you can do some pretty elaborate things because you can then have multiple CNAMEs on top of that DNS entry and have a reverse proxy like CADI or HA proxy or traffic running on the first virtual machine or first host, and then yeah, route to multiple services in your home lab from the outside. Or you can find some non-profit. We have a couple in France, which can provide you a tunnel with a fixed IP address at the other end. That's also something you can do. So the fixed IP address will be on the tunnel end, and then you will VPN out of your network to that tunnel provider. So when your IP address changes, you just reconnect the tunnel. It's almost instant, and the same IP address always points back at you. If you're lucky enough to live in a European city, probably in other places too, but in European cities, it's really becoming a commodity and really cheap. You can get a dedicated fiber from a data center straight to your home, and do BGP on that, or at least have a bigger block than just one IPv4 assigned to you by an ISP. To give you a ballpark idea, where I live, I can get a dedicated 10 gigs fiber for less than 1,000 euro per month. Of course, it's a lot of money, but to be totally self-hosting multiple services, it's totally possible. Then you can get an ASN, IPv6 block GOMS basically for free with that. So that's 1,800 euro yearly. And be careful because the RIP NCC likes to update the pricing model yearly now. We had some pretty bad surprises recent years. Or you can get someone to sponsor you, and they will charge you like 100 or 200 euro per year and do the right things for you. So yeah, you can get an IPv4 block of your own. And I would say if you go like full scale home hosting with a dedicated fiber, keep your DSL or FTTH cheap connection and use that for out-of-band management. It's always good to have an independent connection. So if you're away from your place and you fuck up your BGP or routing configuration, you have a second connection that only accesses the management plane, and you can regain access and reconfigure everything from there. And also it allows you to isolate the management from the public traffic. So even if someone breaks into one of your servers, you will always have this out-of-band management totally separated and secured. Or you can simulate all of this with a couple of VPNs. As I said, some friendly ISPs can provide a VPN, even BGP of a VPN to you. Also, if you have only IPv4 and you want to play with IPv6, you can go to ipv6.he.net. That requires a fixed IPv4, but you can have an IPv6 blocked from Hurricane Electric routed to your home. To be ripe, and I believe this applies to all the other regions as well. You don't have to be a company or an association. You can be also a private individual. I give two examples here. These are two friends. One has a direct connection to 1000 plus other networks from his home. The other one has less peers, but has 100 gigs fiber to home. As I said also about the transatlantic fibers, that applies to your home fibers. If you own both ends, so if you have some small data center space and a fiber going to your home from that, you can plug 10 gigs optics at the end today. Tomorrow you can upgrade to 100, 400, 800, whatever you want. There is no capacity limit on the fiber. And you can also use different colors of light. It's called CWDM or DWDM for course. And I don't remember the D anyway. Yeah, you can use multiplexers to use different colors of light on the same fiber. So the capacity is basically unlimited. And there are 3,000 new ASNs each year, so it's not, what I'm talking about is not something marginal. There are actually people building new networks, interconnecting, and yeah, the internet is growing. There are new participants every day. Also keep in mind that this community is very open. A lot of things are happening in real life. There are NOGs, network operators groups, in almost every country. There are meetings. In France, it's quarterly. In America, NANOG is meeting monthly, I think. The regional internet registries organize many events. So yeah, there is like every month there is some event you can go to, meet with other people, interact. There are a little bit Bitcoin and crypto unfriendly because it boils the oceans, but there are many Bitcoiners who participate as well. So I think the message is going through, and this will end soon. These are a couple of pictures from my friend's home lab. This is a CWDM multiplexer, so you can see there are 4 different colors. Here, of course, the colors are not the actual colors of the light, it's all infrared, but different wavelengths of infrared. And the line, this is the outgoing connection to a long distance fiber. So you can easily connect 40 to 80 kilometers fiber and multiplex different signals over it, and then have your routers and servers behind that. A few years ago, I made an experiment. Probably all of you know 8.8.8.8, which is Google's public DNS server. And as you might have guessed, it's not a single computer. It's actually big farms of servers in many places in the world. Nothing in the internet and in BGP says that one IP block has to be in one physical location. It can be announced in many locations and point to different servers in each location. That's mostly used for UDP single message applications, which DNS is one. So yeah, there are many server farms everywhere announcing the same subnet 8.8.8.0/24. That's called Anycast, as opposed to Unicast. Unicast is when you're announcing a single block in a single location. Anycast is when you're announcing a single block in multiple locations. Usually we don't like to do that for HTTP because it means if this server goes down, I'm starting talking with this server, I have a TCP connection established, and then suddenly this one continues the conversation and has no idea what I'm talking about because it doesn't have the beginning of the TCP conversation, not even talking about the application session and so on. So usually what is done so 8.8.8 is particular case because it's for just public DNS, but let's imagine I'm a CDN. I want to route my customers to the closest server. I will be announcing, let's say, nodal.eu on my Anycast DNS servers, and then each of these servers will answer a different IP address to point the user to the closest server that actually contains the website. So yeah, when we ping these locations, we will notice that if we ping from here, we'll be very close to the server here. If we ping from here, we'll be very close to the server here, which proves that we are not actually talking to this one because the latency would be much bigger. And yeah, in 2019, I decided to do Anycast Bitcoin server. Just to see what would happen. So I used one of my /24 networks temporarily to run one Anycast Bitcoin server, which was 85.2.8.69.13. And when I do a trust route to the server from Geneva, I see it's 2 hops away with almost 0 millisecond distance. When I do trust route from Paris, 1 hop away, zero millisecond distance. But the distance between Geneva and Paris is 9 milliseconds. So yeah, this proves that I'm actually talking to a local server, even if it's the same IP address. I'm actually talking to 2 different servers, like magic. Why do that? Because it allows for geographic load distribution. In the case of a CDN, it also allows you to, if the content is cached in the CDN, the content is closer to the users. For resilience, because if one location goes down, I will be automatically, thanks to BGP, going to the second closest one instead. And also for DDoS absorption, because it's basically it's absorption, it's missing R here, because it's basically the only way to distribute the destination of an attack. DDoS will be trying to attack one single IP from many sources, but using Anycast, you can have many destinations for one attack. And maybe it could replace DNS seed for Bitcoin. We can have a huge network of 8.8.8.8 like Bitcoin servers and use that single big Bitcoin cluster to seed all other nodes. How can I obtain an Iraqi VPN IP address while maintaining maximum anonymity? Where you would have probably to find an Iraqi VPN provider, or even better, an individual who could give you a VPN access to a computer running in their network, paid with Bitcoin, and yeah, use multiple levels of Tor or go to a public hotspot, connect from there. I'm from a generation where when we needed to anonymously post something on a forum, we would just take a plane, travel to another country, post and come back. Why does my Proton VPN connection show a Singaporean location when I'm connected to an Indian server? Because there are multiple sources of truth for the IP locations. You probably heard about GeoIP databases. MaxMind is one of the most famous ones, but there are many others. The regional internet registry Whois database is also one. So if you type Whois some IP address, you will see a country. Some people base things on that. Some people don't. Some people like MaxMind try to determine where are the actual users located behind an IP address. So, for example, for Host4Coins, I had a lot of Russian users using my service for VPN. And my whole French block was considered as in Russia by MaxMind, because by studying latencies and different queries going out of my IP addresses, they determined that the users are in Russia. So yeah, depending on which GeoIP database is used, they use different criteria. There are some initiatives to try to make it more accurate, but at the end of the day, you can't force anybody to believe any database. So yeah, depending on the website you checked, the origin of the IP address Proton VPN gives you, depending on the database they use, you may be getting different answer. And I really invite you to try different GeoIP services and see if you get the same answer for them. If you get a consistently the same answer, you can contact Proton VPN and tell them that there is an issue with their IP address being miscatalogued. From a sysadmin perspective, BGP is not totally useless as well, because actually in modern hosting networks, usually we have BGP to the host or even BGP to the container. I will just let you look at the links I'm providing in this slide. I will not go into the details, but that's a totally very fascinating but totally separate topic. But just, yeah, even if you don't want to do like internet networking, if you manage any big hosting infrastructure, you will be doing some BGP at some point. So almost at the end, some takeaways. There is no single point of control. There is no accountability except trust through reputation. It's a very small engineer-based community, mostly composed of NOGs, network operator groups. Most people act in the best interest of their users. ISPs mainly 99% of ISPs defend net neutrality because they would be just losing customers if they wouldn't. So unless you're in a place where you don't have a choice of ISP, you can assume that the engineers are doing their best, even when the management doesn't necessarily follow their opinion. Yeah, it's the network engineer at the end of the day is the person making the decisions. And don't let all of this scare you. It's a very benevolent community. I started very small, very long ago. I had friends teaching me how to configure routers. I started with recycled computers. As you will see on my last slide, the Zurich Nodal Cloud Network still runs off the BGP routers are actually old x86 based boxes which we recycled and using as routers. Yeah, a couple of opinions. I basically said already all that, but one funny thing is here, if they can do it, you can too. There is a primary school in Zug in Switzerland that have their own AS for absolutely no reason. So yeah, if they can do that, you can too. And I'm here to help as a community member, as a company. If you want to go really serious, I've already did it for several companies in the space. I built the whole, help them build their whole network, acquire the servers, find the data centers, and so on. My contact info, you will find them in the presentation. And for those lucky 50 who got another cloud VPS servers for the Plan B training, this is the actual picture of the server rack we have in Zurich. And this is where the 50 servers are physically located, on these 4 servers here. This is our networking stack, the same as you've seen on the other picture, same switches. Here are some older servers we are using for general purpose compute and running a massive amount of Bitcoin nodes on this. Out-of-band management router and switch. And these are old HA proxy load balancers, which we recycled, installed OpenBSD on them, and running BGP routers on them. Can intelligence agencies like the FBI or NSA still track down Satoshi using old records and data? Well, if we could find somewhere the IP address from which was broadcasted the first Bitcoin transaction, and if the ISP still has records of who was owning this IP address at this time, which to my knowledge, no country in the world requires any ISP to hold these records for so long. In theory, yes, we could find at least which ISP subscriber corresponds to the first Bitcoin transaction. I don't know if that would help to find Satoshi.
Great, thank you. That was a pretty dense presentation about the internet infrastructure.
Yeah,
So
so I tried to not make it too scary, but yeah, unfortunately it is technical.
yes, with a lot of acronyms, and also I think this is the most scary thing, is to be just drawn into a lot of acronyms. But I guess it's kind of the same thing when you start learning about Bitcoin and
Yeah, and you know
anything technical
what's
related.
fun is because in our everyday work we use all these acronyms, and most of them we don't even remember what they mean. We just use the acronyms as words. So
Yeah, yeah, but that was really nice, really refreshing to have all this very synthetic presentation of the infrastructure. I'm so amazed about how resilient the internet can be and how little we can know when we don't interest in this kind of about how it works, and because everything seems to kind of work on our laptop, but there's like so many an iceberg, an entire iceberg of infrastructure below it, and it is very nice to see
yeah,
all of
and you
that
know
here.
even I have 10 and 13 years old kids, and it's very funny when we talk like they still don't understand like Wi-Fi versus SIM card versus internet. Like, okay, I don't have a SIM card in this device, so it doesn't have internet. No, yes, it does. It's yeah, the level of understanding is very, very interesting to see. I love this question. If data centers start to operate in space, would there be problems in terms of timestamp in networking? Okay, I don't fully understand the end of the question, but let's first of all debunk the data center in space thing. It's very impractical and probably will never happen. I can find, let me try to find the video real quick. I will send you the link in the chat. Yeah, this one. So the two problems, as you probably know, space is full of nothing. And to cool down things, we need to exchange the temperature with something. So cooling in space is basically impossible. And in this video, the guy calculates how much, explains how much surface the International Space Station uses only to cool about 800 watts of power. So at the scale of a million watt data center, it's totally impractical. It would have to be basically the size of a planet. Because you have no conductive cooling, you have only how it's called, rayonnement, convection cooling, and yeah, it's much slower. And also the infinite energy from the sun. Just count how much square meters of solar panels you would need to power one rack of servers. Yeah, it's impractical. Even with 100% efficiency doesn't matter here because just the amount of watts per square meter coming from the sun is actually pretty low. But yeah, just to address the timestamping thing, I don't know if you mean like Bitcoin timestamping or in networking itself. In networking itself, I don't see any issue because we are used to very high latency communications. But for Bitcoin timestamping, you can maybe try to find a 2017 talk from Peter Todd about sending the mining capacity to space at Breaking Bitcoin in Paris. And you will get your answers. The big challenge in Lightning Network for me is really the routing calculation of the routing, since you can't know if the whole route has the capacity to route your payment, and multi-path is also very complicated because you have like to try to guess, and yeah, it's a lot of guesswork, and something that could probably be done is something I imagined as an extension to BGP for VoIP 20 years ago, was to announce communication costs per destination inside of the BGP protocol. So maybe something similar in the Lightning. I'm not sure that wouldn't actually decrease the privacy though. So yeah, just routing A to B going through C, that's pretty easy, but A to B going through C, taking into account the capacity of the channels, that's very hard. Yeah, we need some good mathematicians and or programmers on that problem to improve that, because right now I don't know how long you are using or trying to use the Lightning Network, but I started my company in the Bitcoin space because I believed in Lightning Network, and right now we almost have no Lightning users anymore.
How do you evaluate this to say that there's no more user of Lightning? It's more like node
Just use
runners.
yeah, nodal owners, because we release nodal basically to have an always-on node to run Lightning and BTC Pay server to accept payments through Lightning, because it's mostly required to have an always-on node to receive payments without having to connect every time someone wants to pay you. Yeah, all the users we have now, I mean, it's mainly based on support tickets we get. It's all about Electrum server, about Dojo, about on-chain transactions, but yeah, like it's been a very long time we didn't have any support requests about anything Lightning related. So either it works very well, which I don't believe based on my own experience, either people don't use Lightning, and the few users I met at conferences, none of them uses Lightning. They use Wallet of Satoshi, they use maybe Phoenix, some of them. But yeah, we'll see what happens now, because Wallet of Satoshi closed the custodial service in the US and in Europe. So now when I have to use Wallet of Satoshi, I VPN into Switzerland.
Yeah, I saw that.
Yeah, what do I use instead of Lightning? I don't use anything instead of Lightning. On-chain is so cheap right now, it doesn't make sense to use anything else.
Yeah, for sure. I quite agree.
We'll
Although,
see when fees goes up. Yeah.
yeah, I think this is the thing is it really depends on the external environment for which
Mm.
type, like at which layer it is more effective to pay or to transfer something. On a personal note, I would add that on my side, I'm fairly only using Phoenix, and it's pretty well. It works pretty well. Like in terms of UX, and also the rate, the failing rate is quite low right now compared to what it has been a
Mm.
couple of years ago.
But see, Phoenix, if I remember correctly, is a hub and spokes model. So you are just
Yes.
connected to them and then they relay the transactions.
Yeah, I agree. But and this is where it was my second point, is that I'm having a Lightning node at home, and recently I tried to connect it like to connect it to LNbits, which I already tested a couple of years ago, and it was awful. And this time it was way more pleasant to use, and it works. I implemented a couple of mini project a couple of weeks ago based on that, and they all work pretty well. Thanks to I think what really changed is that now there's a lot of people at least there's a couple of people offering LSP services. Like you can borrow some liquidity against some SAT, and it makes things a bit
Mm.
easier to manage your liquidity. But for sure, it's not the
So
best
see,
thing.
One other thing that makes me pretty pessimistic about the state of Lightning is as a merchant, I have 4 or 5 Lightning nodes on which I receive only payments. I had channels open from LN Big for a very long time. And one day, at the same time, all the channels got closed by LN Big. So I started looking into other LSPs. I got one channel from Zeus. How is called his service?
It's
Anyway,
Olymp quelque chose.
oh
Uh,
yeah, Olympus. Yeah, Olympus, I think.
Olympus.
So I am very happy with the service. It works for me, but guess how many channels are on the node of Olympus?
How many channels you said?
Yeah, how many channels Olympus has?
I don't know.
5.
I would say like 5, only 5 of them. Yeah, but it's 5
Yeah.
public. Mostly it will be
Yeah, yeah,
private.
yeah, yeah.
Yeah.
The customer channels are private, and unfortunately, they offer only private for customers. So
Yeah. Yeah, but what I mean is that for not really high intensive use, the LSP model works at least not that fine, not that bad. So I would just, based on the comment of Bainon, I would just mention regarding the list of the first 31st student. We have settled the list. I already shared it to Michelle, and you will be receiving an email with all the documentation and how to start accessing your VPS for this period. Know that maybe Michelle, you can talk a bit about it, but it's a brand new services that Noodle is offering, and you kind of part of the first users for that new service. So thanks for them for being part of that collaboration, of that partnership for the Plan B program. Maybe you
yeah,
can share a
so
couple of words
historically,
again.
yeah, historically on the Nodal Cloud service, we were only providing the same stack as on our physical devices, which is a 4 Bitcoin node with Lightning, BTC Pay Server, Dojo, Electrum, and so on. And yeah, as part of this partnership, we decided to test providing just empty VPS Ubuntu servers. I don't remember the characteristic, but I think you get 4 cores, 8 gigs of RAM, 128 gigs of SSD. You can do whatever you want with them. You are root. I mean, you are sudoer. You can become root using sudo. I prepared a small PDF documentation with a few screenshots. So I took the liberty to pre-register all the 50 email addresses in the database. These emails will never be used for anything other than sending messages from the website when something happens to your server, to be clear. So the way it works, you just go to nodo.cloud, you reset your password because there is no password set on the accounts. They are locked right now. And then, yeah, you have a couple of instructions to set an SSH key. The server will reboot with your own SSH key, and that's it, and you can start using it. And for the other participants, we will be, as soon as we make this service public, which is in 10 to 15 days, we'll give you a discount code that you can use, and you can also use that discount code if you want to keep the server after your training. So yeah, the public price is 25 euro per month, but you will be getting a discount as a Plan B Academy student.
Yeah, thank you a lot for it. I think that would be nice. Note that this it will not be mandatory for all the students to have access to a VPS. We'll just propose what I'm preparing for you is that I will try to create some kind of additional kind of exercise where you can do it on your own machine on local regarding the lecture that we will have during this masterclass phase. And for those who have access to this VPS, it will be an opportunity to use it and maybe to test it. This kind of exercise, I will mention everything in the Discord channel and also in the on the platform directly on each chapter, and I will mention it to the next lecture. So mostly next Tuesday, I will tell you about what I prepared for you for these first two lecture. There's someone who asking is there's any support of YubiKey for the 2FA. You
Yeah,
said
so not
okay,
right now.
perfect.
We actually use it on our admin side, so it's implemented on the website, but it's not enabled on the public side because we don't have a way to reset the 2FA, so it would generate too much support requests we couldn't handle because we have no way to prove the identity of the user, since we don't ask for any personal information other than a valid email address. By the way, if you want to continue using the service and to pay, you have to enter your billing info. The billing info is just checking the individual box and putting a country. If you put a country outside EU, you will not be charged for taxes. Just a hint.
Hey, cool. Thanks. Do anyone has another question for regarding the lecture or any other topic that could be related to it? Maybe I would have a question for you, Michelle, is that what kind of triggered your passion for this infrastructure interest regarding internet and now here on Bitcoin? Do you have like something that triggered it, or is it something that has been built over the years?
Well, I basically I arrived to France at age 6 in 1987, and one of the first thing I did was to go to the public library and read all the books about computers and robots I could read. So I started electronics basically at age 10, and then from electronics I went to computers, and from computers I went to networks. And Nodal and Bitcoin is a project that I like because it combines all three: networking, computers, and electronics. So I came to Bitcoin through that way, not the economics, not the money, not the. I discovered that much later, but I really came from the electronics and infrastructure side, and yeah, I really liked this this technical object because it combined everything I like in one place.
Okay, so you're
I would
talking
just
about
mod.
like the. Sorry, go ahead.
Yeah, go ahead, go ahead.
I was just trying to understand what you said. Is that what really interested you with, especially with Bitcoin, it was the way it has been thought and design in terms of protocol and network.
Yeah,
Is that right? Okay, yeah. Because
yeah,
it was
yeah,
combining a lot of things at once. Okay, yeah.
yeah. We will never get rid of IPv4. That's a fact. IPv6 adoption is going actually pretty well, especially in Western Europe. In Asia, less so in the US. But there are some major services that are still IPv4 only. Until recently, GitHub was one. AWS didn't support IPv6 for a very long time. I was part of the first associations to push IPv6 adoption more than 20 years ago. We gave up a long time ago now because, yeah, it's there are several problems of IPv6. First, there are many equipments that will never be upgraded and that support only IPv4. Second, is already hard to remember on IPv4, so not even talking about IPv6. Third one is IPv6 was thought by people working in universities with no practical knowledge of the internet, and they design a very complicated protocol that has security flaws that are unfixable by design. So there are some vendors that try to address these issues through high-level patches, but there is nothing definitive that can fix the design flaws. So yeah, it looked nice on paper. It's like data center in space. It's impractical to use in real life. But all the servers you are getting and all the servers I'm running are dual stack IPv4, IPv6. That being said, if you want to use Tor and if you want it actually to work, I invite you to disable IPv6 on the server. We've seen some cases where Tor is completely fucked up by using IPv6. Yeah.
Okay.
That's another 2 hours topic just about IPv6 probably.
Okay. And maybe do you have any opinion on the way the layer model is doing with internet and the parallel that we can do with Bitcoin also being trying to be built this way, and the relation with the kind of the arrow of decentralization, like from the bottom part trying to be as decentralized as possible, and on the upper part getting more and more centralized. As you said, like the use of the internet uses that we have is pretty centralized, but the infrastructure itself is decentralized. Do you think that the way Bitcoin is being built and will be built in the future will also follow this kind of pattern?
I actually completely forgot to talk about a very important topic. Let me share
So
another window real quick.
we will have another 2 hours lecture. Are you ready? Are
No,
you
no, no.
ready,
This
all?
is this is a pretty short one. In Bitcoin Core, there is something called AS map. The AS is exactly the AS I talked about before. So by default, I think it's still disabled, but you can enable it with a single flag. Bitcoin Core will privilege connections to other nodes running in other networks. Meaning, if you enable this, you will not connect to more than one Bitcoin node running in Amazon, not more than one node running in Google, and so on. That's also why it's important to have as many Bitcoin users running their own networks and ASNs. So we have this diversity, and we have Bitcoin nodes in separate networks.
We
Why
have
the
two
network
other
architecture
questions.
has not changed since 95, as you mentioned in the beginning, due to the physics limitation? No, it's not a physics limitation. It's one of these things that are good enough and don't need to be upgraded. And also, changing BGP today would mean changing 100% of the routers of the internet, which, as I said, let's say $500K to $1 million per router, multiplied by probably 1 million. Yeah, just not upgradable by design. It's like why cars have 4 wheels and go on roads, because it just works. And if we wanted to change that, we would have to replace all the roads and all the cars. I don't know FIPS. I know FIPS, but I know another FIPS, the security standard. I'll have a look at that. But from what I see from the very beginning, yeah, it proposes serial and radio as other base layers. But the main problem with many of these high-level crypto/Bitcoin-based networking projects is they tend to forget that they are running on top of the internet and how the internet itself works. So yeah, you will never be layer 0 or 1 or 2. You will always be above layer 3 or 4.
Other question coming.
Well, speaking of mesh, we tried to make a demo of sending a Bitcoin transaction over Meshtastic in Prague pretty recently with a friend who is a ham radio operator and a very smart person. It took us 2 hours just to manage to send one single transaction because the maximum size of a Meshtastic message is too small. So yeah, it's nice to try to run things off top of other things, but if you ignore how the underlying things actually work, it's pretty much doomed to failure. One thing you must know for unregulated mesh networks is that the quantity of data you can transmit is very small per unit of time. So yeah, you can't do much with that. I'm actually working now on sending Bitcoin transactions over satellite using some IoT satellite services. But that too is very, very small. You have to retransmit a lot because the satellite is not always above your head. The upside is it's a very cheap and small hardware and antenna. The downside is so limited that I'm not sure I will succeed in sending even a smallest on-chain transaction. Potential limitation noise, Wi-Fi router, positive or negative, tailgate. Oh, I get don't start me on that project. One word about Tollgate, because I've met the guy on several occasions and we agreed to disagree. Making anybody pay for Wi-Fi in 2026, I don't see the point. You get basically free GSM roaming all over the world and free Wi-Fi everywhere. So I don't see. I mean, it's a nice pet project, but the routers he's using are so underpowered that anyway, you will not get any serious bandwidth out of them. And yeah, I would never pay for Wi-Fi anywhere. And I've traveled to countries where internet is very hard to get. I prefer to pay silent link and get eSIM in my phone and have internet everywhere instead. Other than that, Wi-Fi is right now, Wi-Fi 7 is faster than a gigabit wired connection. So yeah, no issues using Wi-Fi for anything, really. And yeah, what was fun is we talked about Tollgate, and then he said, well, maybe on a plane, and blah, blah, blah. And on the plane back from, I think it was from Riga, we had free Starlink, 300 megabits per second during the whole flight, door to door. So yeah. And more and more airlines are deploying Starlink now on their planes for free.
Right. I think if it's all for you, thank you again. That was really I really appreciate
Thank you for
the
having me. It was a very interesting exercise. And if there are any follow-up questions, don't hesitate to forward them to me.
yeah. I will do such. Thank you a lot. And for the rest of the students, we can continue the discussion on the Discord, and just like Keto said, you can send him even. I think you shared in your note the
Yeah,
your
you
email, so you
can
can be
send me an
reached
email
out. So
direct.
yeah, thanks again for the partnership, and see you soon.
Thank you all.
Bye.
Have a good evening or day. Bye.
Yeah, stopping the recording. Up.